At the end of the last video, I talked about this partinomial coefficients. I don't know if that's the best name for this, and open to better. But basically, the brouhaha is all about how you can slide the partinomial coefficients triangle out from under and slide the Pascal's triangle in its place, and all of the operations that take place on top remain the same. So that in these angled lines, we're summing the Fibonacci numbers. The rows are summing the powers of 2. But over here, the same slanted lines are summing to partitions, and the rows are summing to over partitions. So creating this isomorphism right off the bat. But there's a lot more to it, because look at this one here. This is well, first of all, I've got 4 different types, or 4 different sloped lines running through this triangle. This is still officially the partinomial coefficients triangle. It's just been crunched down to a half. It wasn't necessary to do that, but it shows that basically if we uncrunch it, then and keep these functions the same, it's just going to change the slope of the lines. Nothing's going to go away. It's all still going to work. So let me see if I can't get a bigger view of this and realize, folks, I've been talking and nobody can see anything. All right, so we're getting basically, so like for example, here basically the point being is that you have one copy of the partinomial coefficients triangle, and you have one copy of the binomials on Pascal's triangle, or of the Pascal's triangle, and you determine the slope of lines running through it by alpha beta, and all of the lines that intersect points, whatever points are intersected by those lines, add them up, and that gives you the answer to your function. So here, and you can do this with a single copy of these triangles to compute all of the partition generalized alpha beta partition numbers, and using Pascal's triangle, compute all of the alpha beta generalized Fibonacci numbers. What are those? Well, show you here in a second. Let's start with this one first. And so, but this is just a demonstration. Here we have P13 of n. We have P12, which is of course unrestricted partitions. We also have P23 of n that we can do out of here with just by adjusting the slope of the line that goes through. And on the bottom here, we have over partitions. That was rows of Pascal's triangle before, the rows of the standard partinomial coefficients triangle. And this is just a reflection of how these things get morphed when you play with the angles. So here then is this really the same graph as that, only now the binomial coefficients triangle, Pascal's triangle, is slid in place of the partinomial coefficients triangle. And on the bottom, where we had over partitions, we get powers of 2. And all this is starting to make sense now, because we get here general Fibonacci numbers, f13 of n, and those are going to be given by the recurrence f13 of n minus 1 and f13 of n minus 3. The first 2 terms of what otherwise is the same thing as the partitions recurrence. So in a way, Fibonacci numbers are the first estimate term of a series that converges to partitions. We could look over here where we had unrestricted partitions, P12, and it's F12 here, Fibonacci numbers, which is just the standard f is given by f of n minus 1 plus f of n minus 2. And here, Fibonacci numbers, generalized alpha beta Fibonacci numbers, f23 will be the recurrence will be f of 23 of n minus 2 plus f of 23 of n minus 3. Real simple. But what it does show us, very interestingly, is that what would be the f11 Fibonacci numbers. Well, 2 times 1 plus 1 is going to give us 2, and then 2 times 2 plus 2 is going to give us 4, and then 2 times 4 plus 4 is going to give us 8, etc., aka the powers of 2. So there's a very real sense in which we can say that the powers of 2 are over Fibonacci numbers. Can you believe it? The powers of 2 are over Fibonacci numbers. Huh. Very interesting. And again, now on Pascal's triangle, we can then compute any of the generalized Fibonacci numbers, and we can do more than that because this is like the first. Let's say this is the first term, the k equals 1 and the k equals -1 terms of the recurrence for partitions. So Fibonacci's are just a truncated partition recurrence. If we add now the k equals 2 and the k equals -2 terms, well, like in the case of the 1, 3s, we had n minus 1, n minus 3, and we know that that sequence is the triangular numbers, so the next ones would be minus f of 1, 3 of n minus 6 minus f of 1, 3 of n minus 10. Now that would be 2 terms of our converging sequence. Our sequence is converging to the partitions function itself. So Fibonacci's are the first element or the first term of a convergent series. And then we could say that when we add like the n minus 6 and n minus 10, or subtract the n minus 6, n minus 10 terms, that we've truncated that partition recurrence at k equals 2. And so that would be the k alpha beta generalized Fibonacci numbers. We could say that k1 3 of n is going to be given by the recurrence with those first 4 terms, or the first 2 pairs plus minus, and that's where our k equals 2 comes from. And so we can see as k goes from 1, the Fibonacci's, up to n, we converge on the partitions function. So we've got kind of the same function here, or the same. It's such a fascinating thing. Such a fascinating thing. So there's the partinomial coefficients triangle. You'll notice that it matches Pascal's triangle up to the 3rd degree, and then the 4th degree we're just really missing 1 and 1, and you'll find that we're missing 2, 2, 2, 2. And the recurrence is going to follow the recurrence for partitions over partitions of n, because this is a recurrence, 1 and then 1 plus 1, and then 1, 1 plus 1, 1, and then 1, 2, 1 plus 1, 2, 1. This is just doubling every row. It's doing that for partitions up to a point, but then our recurrence says, well, hey, wait a minute. At degree 4, we have a square, so that's one of our quadratic numbers. So now we must subtract the term at k equals 0, which is 1, but there's 2 copies, so we're subtracting 1 here and 1 here, and then 1, 1 here, and then 1, 1 here. This is the recurrence for over partitions, where we've got 2 identical terms but separated from each other in terms of where they add, and it's really quite fascinating. And we can do something similar. Now we have here the partitions, partinomial coefficients triangle multiplied by 1, and then another copy multiplied by 2 and added in at this point, etc. So across the top we're following our sequence for sigma as given in terms of partition numbers to get sigma sum of divisors. And similarly, as we had before, we could change up the slope in accordance with alpha beta and get whatever restricted sigma alpha beta n function values we like by just adding up the numbers that are intersected by the line of the slope that we determine. And it reveals, if you look at this, you know, any slope going through here is going to be going through a section where it's being added, increasing, and then numbers start getting subtracted, so it's decreasing, and then maybe there's a section with a section of zeros where it's flat, and then starts increasing again. And this does indeed happen. These regions of zeros get larger and larger as the distance between the positive and negative side of the quadratic at plus or minus k, that just does nothing but grow. And the instances of an integer that is also a value of the polynomial, the density just goes to 0. So in a sense, we're getting a lot more zeros than well, that's not exactly true, because but anyway, long story short, we can think of this in terms of like a temperature, and like this is the temperature is rising, and then it peaks and levels off, and then it goes down, and it bottoms out and levels off, and then it goes up again, and this is like spring, summer, fall, winter, spring, summer, fall, winter, which is really interesting that sigma, the sum of divisors, has seasons, has distinct seasons with pivotal with equinoxes, with specific equinoxes. And then here's an example, and this is the case of the squares. So this is would actually sort of maybe be corresponding to over partitions or powers of 2. But basically what this is looking at the sequence of consecutive numbers from x squared to x plus 1 squared minus 1. So that's 2x plus 1 numbers. And for each of those, we're going to compute the sum of divisors of that number, and then we're going to divide by that number so that we have a sort of ratio of sigma per, a density of sigma, or estimate of sigma for the given n, which we expect to follow log n or what have you. And then, so we're going to add all of those ratios together, and then we're going to divide by the number of ratios we have to get the average of basically sigma n over n, which is the quantity that's used in the Robin-Lagarius criteria for the Riemann hypothesis, for example. And that's zeta 2. It converges to zeta 2. The more numbers you include, the more consecutive numbers you include in your group, in your averages, the closer it's going to be to zeta 2. So what makes a difference between warm and cold here is that in the warm table, x is always odd, and in the cold table, always even, and in the cold table, x is always odd. So we have about 300, we're taking 300 spans of between squares of consecutive numbers and averaging their ratio of sigma to n, sigma n over n. Each one of the data points in here is to approach zeta 2, but from above, and the cool does approach zeta 2, but from below. And so these are just intertwined spans of the consecutive numbers between squares, and just to show that this behavior continues. This is x equals 12,000, so you're really talking about each one of the data points is an average over like 24,000 numbers. Thank you again for watching my video. Please check out the comments for a PayPal link where you can support me and my research. I kind of want to go get something going on with some people to accelerate my scholarship and my learning, but also to teach what I've found on my own over the last 20 years, and which is just coming into fruition as I've learned enough about modern mathematics to understand what it is that I've been playing with this whole time. So that's my deal. Hope you like my video and my theorems and all kinds of things, and I hope you support my research. Thank you very much.